calculate the pH of a 0.010 molar H2SO4. So this is pretty dilute, 0.01 molar, a lot less than, a lot less than 1. So we can't ignore the second dissociation. Okay, so let's take a look at what we have. We have our major species. And again, we have the H plus from the first dissociation, we have the HSO4 from the first dissociation, and we have water. These two are going to dominate the equilibrium. We know what this is already. This is just 0.01 molar because it's fully dissociated, strong. The final hydrogen ion concentration, is going to be 0.010 plus X, and X is the hydrogen ion concentration we get from the dissociation of the HSO4 minus. So that's the equilibrium we want to look at. HSO4 minus goes to H plus SO4 2 minus. We have initial, we have change, we have equilibrium. The initial concentration is 0.010, right? And 0.010, strong, dissociates into this and this, first dissociation. This is 0. The change is minus X. Plus X, X, we get 0.010 minus X over here. We get 0.010 plus X over here. We get X over here, and we write Ka2, which is 1.2 times 10 to the negative 2, is equal to 0.010 plus X times X. Oops, let me just take out this parentheses here. Times X. And then that's going to be over 0.010 minus X. That's it. We have to solve this equation. Multiply through, get your X squared, get your X term, get your, it's going to be AX squared plus BX plus C equals 0. B and C and A, they can be negative if they need to be. And then you just plug it into the quadratic equation, or use your graphing utility, your TI-8384 calculator, your graphing calculator, to find the roots of this equation. Now, you're going to get two roots. Check to see what makes sense. One of the roots is completely not going to make sense. The other root will make sense. And that's the whole idea. So, your final hydrogen ion concentration, oops, let's make this a little bit. When you get X, you're going to get X equal to some number. We'll just put a little box there. Your final hydrogen ion concentration is going to equal the 0.010 plus this boxed number, and your pH is going to equal the negative log of your final hydrogen ion concentration. And that's it. So, for polyprotic acids, treat them like any other equilibrium. Usually, most polyprotic acids are weak acids. It's going to be the first dissociation that dominates. You can pretty much ignore the second, third, fourth. I don't even know if there is well, there is, but weak acid, you can pretty much ignore the second and third dissociations. For sulfuric acid, maybe, maybe not. If you're talking about 1 molar or above, you can ignore the second dissociation. If you're talking about more dilute than 1 molar, 0.8, 0.7, 0.6, below that, the second dissociation is going to contribute a significant amount of hydrogen ion. So you have to take the amount that comes from the original concentration of the first dissociation, find the amount that comes from the second, add them, and then take the negative log of that. So I hope that helps. Again, you see it's pretty much all the same, slightly different when you're dealing with multiple dissociations in the case of sulfuric acid. Thank you for joining us here at Educator.com. We'll see you next time to discuss the acid-base properties of salts.